Welcome to Empowered Learning. This is the first video in the video series for applications of exponential and logarithmic equations. So in this part 1 video, we are going to specifically talk about compound and continuous compounded interest. Okay. So first we want to go over the formulas for compound interest and continuously compounded interest so that we see the similarities and differences in between them, understand what all the variables mean, and then after that we're going to go through a series of problems sort of exercising using these two formulas. We're also going to talk about a concept called effective interest rate. Effective interest rate, I should say. Another way or another name that it's known by is annual percentage yield. All this really means is that we're actually figuring out the true interest rate someone is earning or someone is paying, depending upon if you're investing in money or if you're borrowing the money, based upon how much money goes into the investment or how much money is borrowed, and what the return is or what the payback amount is. So that's what that is. So that'll be the three major concepts we will be talking about here. So first, let's go over compound interest. So we see that the formula is A equals to P times, and in parentheses, R1 plus R divided by N, all that in parentheses raised to the N times T, where A is going to be the accumulated amount or the future amount of whatever P is going to grow into. If this is an investment, if you're borrowing money, then of course P is going to be your principal or initial amount that you borrowed, and A is what you'll eventually be paying back. So N is what's called the number of compounding periods per year. And here that's based upon a certain interest rate. So here it says number of compounding periods per year, that interest I, which is R divided by N applied to principal. And so what this means here is that we're actually looking at this as interest per compounding period, or interest rate per compounding period. For example, if we say N is equal to 1, then that means that we are compounding the interest that's being earned on this initial amount here one time a year. Okay, so that means, let's say you invest money on January 1, at the end of December 31st that same year, it's time to now take whatever interest that has been earned on that money, collect it, and then it gets added on to the principal, and thus at that particular time, that is what A ends up being, okay, for year T equals 1. Now, let's say if we wanted to compound 4 times a year, then that means you're compounding quarterly, okay? So I'll erase this. Quarterly. So that means since there's 12 months in a year, at the end of every 3 months, we're taking whatever interest has been earned during that time, applying it or adding it on to the principal, and then whatever that amount is plus the principal becomes the current A value or future value. Okay? And that happens 4 times a year. So every 3 months, whatever interest is earned on whatever the current principal is at that particular time, it gets added on to it, and it just keeps repeating itself. Okay? And so this little I that you see here is what the actual interest rate is per that compounding period. And just to kind of give you an idea of what that is, let's say you have an investment that's supposed to pay 10% per year, but we say that the interest is compounding twice a year, okay? And so if it compounds twice a year, then it means that it's compounding semi-annually, okay? So let's say it does that. So in that case, then the interest rate per compounding period is going to be this 10% divided by 2, which is actually 5%. So that means at the end of 6 months, whatever initial money P you had in the investment or you borrowed, is going to have an extra 5% added on to it. And then on that day, at the middle of the year, right at 6 months, your new value for your principal is going to be P plus whatever 5% of P is. And then you go another 6 months, and that new amount for P, which is the P plus 5%, is going to have another 5% added on to it. But it's going to be the 5% of the new amount that you had at the 6 month period, once that first compounding of interest got added on. Okay, so that's how that works. So, of course, here R is what we call the annual or nominal interest rate. So that's like this 10% here. And let's say if you're trying to look at some financial instrument or product, that's what you get told that the interest rate is. But you have to pay attention to the compounding period, because that's actually going to give you a clue as to how much interest you're really going to earn. Okay, and so that kind of gets into my whole discussion about the annual percentage yield or effective interest rate that we're going to talk about later. Of course, P is just the principal or the present or initial amount. T is time, and notice that time is something that is always measured in years. And so normally with this particular formula for compound interest, unless we're specifically told that we're looking at time in a different way, if we have something like, let's say, 3 months, then we know 3 months is 1/4 of a year. If we're looking at it in terms of days, let's say we're looking at this as 40 days. Okay, so 40 days, you would have to determine whether you're considering looking at the days in a year as being 360 days or 365 days. And so some financial institutions look at things at 360 days. Some look at it at 365. Most banks look at it at 360 because they have 5 standard holidays throughout the year. Okay, so here, if we had 40 days, then you would have to figure out what that fraction of a year is. If this was some kind of loan, or let's say some investment that some traditional bank is offering. So we would have to do 40 divided by 360, which these zeros would go away if we divide by 10. And this would end up being basically 1/9 of a year. Okay, so that is how we would have to look at that. So with that being said, the last thing that we need to talk about is this product of n times t, and that's what our exponent is here. Essentially, all it is, it's just the number of compounding periods per year times the actual time in years. And that essentially just gives us a total amount of compounding periods that we're going to have for the life of the investment or the life of the loan or debt that we have. Okay. So moving on, we see that continuously compounded interest, what this really is essentially, it is the same as this particular formula here, but the difference is that the compounding periods are getting so small to where, well, the length of the compounding periods are getting so small to where we essentially say that the number of compounding periods that we have is infinite. Okay, so if we're compounding interest every moment of every second of every day, every fraction of a second, every fraction of a second, if we were to actually work all this out here, and if we were in a calculus course, we would take the limit of this particular expression, we would find that when we take the limit, that all the stuff that we have on the inside here minus the p and the t that you have there, this portion right here, if we were to take the limit of that, that would be this irrational number e, which is approximately equal to 2.713. Okay. And so we know in most models where we're trying to model something that grows or decays exponentially, we know that that e appears in these models a lot. Okay. So we nickname this continuously compounded interest formula the PERT formula because of P-E-R-T, and that's just a way for us to remember it. The A is still the future value of the investment at the end of time period T. R, T, and P are pretty much defined the same, and of course E is that irrational number that's approximately equal to 2.713. And here, I've looked at it differently, but essentially this is what E is defined to be. And if I rewrite what I have here, if X was, let's say, R divided by, well, let's say not here. Yeah, got to do it correctly. So if X was N divided by R, then this, what you're seeing here, if I plugged in N divided by R here for X and N divided by R here for X, and then raised all that to the T, then I would have what you see here with that T in the exponent there. Okay. All right. So it's not as important at this particular level to know the definition of E in terms of a limit. I just want to make you aware that for the compound interest formula, there is a ceiling or sort of like a asymptote, as we call it, that this particular value of A will approach. Okay, so it can't go beyond a certain amount for a particular annual interest rate, and so that's the main idea. All right, so now let's look at the annual percentage yield. So the annual percentage yield, or what's called the effective or true interest rate, we're essentially just looking at the difference in between what was originally invested or borrowed and the future amount. So you're looking at this and you're saying, all right, well, if I strip out the P's here, because if you look at this, add them up, well, let's say not add them up. So if we look at these and say, all right, well, let me take the difference in between what I got out versus what I put in, then what you would have is this situation here. Okay, I'll erase that P. Since what we put in really doesn't matter, because, you know, the thing is you're trying to really look at whatever amount of money you had in an investment or in some loan or debt, you want to see what's going to give you the highest interest rate on that. And the actual amount really doesn't matter. So what you could do here is factor out this P. And if you factor out the P, what you end up having is this. And this portion here that actually lets you know what your true interest rate is based upon the money that you put in versus what you put out. And so here, this is what you end up seeing there. Now, the only thing that you see here that is slightly different than what I have here is the fact that you notice I have this T here. And so I just kind of did this on the cuff. We normally ignore time here. And that's mainly because if we go back to what we were talking about earlier up here, it's really this number 1 plus R divided by N, all that raised to the N. This is really the thing that's controlling how fast your money is growing, or how much more money you're having to pay in debt. So the T part, yeah, is part of it, but the part that's really affecting what's going on is everything that I have in this little box here. Okay. And so that's the same thing that you see here in this first term. And that's why the annual percentage yield, or the effective or true interest rate, is what it is. And so the last thing I want you to notice before we begin doing examples here is that we have two different ways of actually expressing this. So one acronym for it is APY, annual percentage yield. In other textbooks, you'll see it as effective or true interest rate, little r sub little e. Both mean the same thing. Okay, it really just depends upon what variable whoever wants to use this comes up with. We could probably come up with some other stuff. Okay. All right. So here we see that, of course, this is the formula for it. Both of these are the same thing, and this is going to be an equation for the principal amount invested and an annual, aka nominal interest rate, R, compounded n times per year. So it's the compounding and the interest rate that really affect what your true interest rate is. Okay? And of course, R and N are the same as what was defined for the finite compound interest and continuously compounded interest formulas. And here, I wanted to also bring this up, is that if we wanted to figure out what is going to be the maximum effective true interest rate, a maximum annual percentage yield, it would actually just be e raised to the r minus 1. Okay? And what this essentially says is that for a particular interest rate and compounding period, what is going to be the maximum amount of true interest you can earn on a particular investment, or what is the maximum amount of interest that's mathematically possible for you to be charged on a loan. And so this formula here, e raised to the r minus 1, actually allows us to be able to know that. Okay. All right. So with that being said, that's the basics on these formulas. So now what we're going to do is get into the actual examples. Okay, so for our first set of examples, we're just going to practice making sure that we know how to convert the annual percentage rate that we're given into the interest rate per compounding period. And we want to make sure that we do that so we actually have the whole idea of having interest rate in terms of a fraction of a year accounted for in our calculations. So first, we want to figure out what is going to be our interest rate here. What is going to be the interest rate per compounding period if I have 9% annual interest rate compounded monthly. So what this means here is that this is our R, and compounded monthly here means that N is going to be equal to 12. So we'll have 9% divided by 12, or if we write that in decimal form, that's just going to be 0.09 divided by 12. And if we work all that out, we'll see that we end up getting 0.0075, which essentially is just 0.75%, 0.75 per 100. Okay. So that is our first one here. So next, 14.6% compounded daily, and we're assuming a 360-day a year here. So here this means that N is 360, and here R is going to be 14.6, and so here this is just R divided by N, 14.6% over 360, and this just ends up being 0.416 divided by 360, and once we do that, what we end up getting is 0.000405 repeating. So after this is just a bunch of fives. And so we'll just approximate that to 0.045 repeating percent. Okay. And so if we wanted to truncate after the first two decimal places here, normally people would say, all right, well, you basically have an interest rate per compounding period of about 0.04%. Okay, but I'm going to keep it exact here. All right, so let's move on to our next examples. So in our example number 2, we're kind of taking the opposite approach here, where we know that the interest rate per compounding period is R divided by N, but now what we are going to be given is the interest rate, and we will be given the compounding period, and what we want to find is the actual or annual nominal interest rate. Okay, so in this case, we'll have I is equal to R divided by N, and here we know that this is going to be 0.395% per month. So that's 0.395% per month. And that's going to be equal to, R is what we're trying to find. And we know, since this is going to be per month, this is going to be 12 here. Okay. And so now if I actually do the math on that, I'm just going to take 12 months and multiply that times 0.395%. And that's just going to be equal to R. Now, and of course, this is 0.395% per month. So let me go ahead and put that there. And here we know that this unit and this unit will end up reducing to 1. And so all that's left is the percentage unit here. And so now all this means is that we just have 12 times, and now I'm actually going to write this out in decimal form. So we got 0.00395. And so from there, we see that this result just ends up being a 0.0474, which is essentially just going to be 4.74%. So that's the actual annual interest rate, if we looked at it as annual interest rate per year. So for our next example, kind of the same thing. We know what we're working with here. So we have this. We know that this 2.1% is going to be per half year. So this will be, and I'm just going to go ahead and translate into a decimal immediately here. So this will be 0.021, and that should equal to R divided by 2, because if we're doing this per half year, that means it's semi-annually. And so now all we have to do is just say R is 2 times 0.021. And that is going to be equal to 0.042, which is essentially just 4.2%. So our annual, aka nominal interest rate, is just going to be 4.2%. All right. So for our last example, have I is equal to R divided by N. And that implies that this 1.4% is going to be 0.014 is equal to R divided by N. And since this is per quarter, this is telling you that N is equal to 4. And so how I'm getting R here, just in case you didn't catch this earlier, I am doing cross multiplication across the equal sign. And that's like a quick and dirty way to be able to multiply both sides by 4 and get the result that you want. So here, if I do that, then I have 0.014 times 4, and that just equals R. And of course, when I multiply that together, this ends up just being 0.056, which is the same as 5.6%. Okay. And so now that we know how to deal with both annual or nominal interest rates and convert them into interest rates per compounding period and vice versa, we now have the tools that we need to be able to move forward and start using our finite compound interest, continuously compounding interest, and APY formulas. All right, so for example 3, this is our first real example in using the compound interest formulas. So if we have $100 that's going to be invested at 6% compounded, and then of course we have all these different compounding periods, we want to know what is going to be the amount after 4 years and how much interest did we earn. So we'll do each of these separately here. We know the basic formula that we're going to use is this one. And what's going to change is the value for N. Of course, annually N is going to be 1, quarterly N is going to be 4, and monthly N is going to be 12. Everything else is pretty much the same. We know that this 100 here is going to be P, this 6%, that's going to be R, and we know that this 4 years here, that is going to be our T. So everything's going to pretty much stay the same. Only thing that's different is making sure that we change the value of N. And of course, as the compounding periods increase, we should see that the accumulated amount here that we're trying to solve for will go up slightly each time. Okay. Now, as far as taking care of how much interest is earned, remember, A is what we get out of the investment. P is what we put into the investment. So the amount of interest earned is going to be the difference in between what we got out and what we initially put in. Okay. And so that's how we're going to look at that. So for the solution here, when we have N is equal to 1, we just know that A is equal to 100 times 1 plus 0.06, because that's 6% in decimal form, divided by 1. And all that in parentheses raised to the 1 times 4. And that's not 1.4, that's 1 times 4. And I may write it like this to make sure that we don't mistake that. Okay. And so once we have all that, then this will just end up being 100 times 1.06 raised to the power of 4. And this ends up being $126.25. Of course, if we know that, then of course the interest earned is just going to be the difference in between $126.25 and the initial $100, which is just going to be the $26.25. Okay. So next, for our solution for B, we know that our compounding period is quarterly, so that means n is equal to 4. We're going to have 4 compounding periods per year, and we just repeat the process. So A is equal to P, 1 plus 6% divided by 4, and this will be, pen got away from me there. It's going to be 4 times 4 now in the exponent. And so now when we have that, that just ends up being 100 times 1.015 raised to the 16. And this is going to be roughly, and I'm putting equal signs here, but really I should be doing approximation equal signs here. And that's going to be $126.90. Okay. So of course here we know that the difference or the amount of interest earned is going to be the difference in between what was accumulated and what was initially put in. And of course this time it is going to be $26.90. So we see just because the compounding period is different here, we're earning about an extra 65 cents total over this investment. Okay. All right, so let's look at the solution for C. And of course, for that one, we said it was monthly, so that means n is going to be 12 this time. Okay. So here we have n is equal to 12. And so the same thing. A is equal to 100. 1 plus 0.6 divided by 12. And all that's raised to the 12 times 4. And of course, that will end up being 100. And that will be times, got away from me again, times 1 point, and whenever I do, so when I do that, that's going to be 0.005 raised to the 12 times 4 is 48, and that's going to approximately equal $127.49. So of course, the interest earned, the difference is of course going to be $27.49 then. All right, so we've got our first taste of using the compound interest formula. The main thing that we see here is that the compounding period actually matters. And so that's one thing that you want to pay attention to if you are going to put your monies into an investment, or if you are taking out a loan, for instance, student loans, they are compounded at least monthly. So know that the interest that's being piled on, that compounding period actually matters. So it's not enough just to pay attention to the annual nominal interest rate. We also need to pay attention to how many times that interest is actually being compounded per year. And so that's one of the reasons, like for a single family home, most people know that if you get a mortgage out on a home, and let's say, and I'm just using easy numbers here, that your mortgage is $100,000, over that 30-year period, if you do a 30-year fixed interest rate, you'll pay more than double the amount for that particular home. Okay, so you may end up paying like $220,000, $215,000 for the actual home, even though you financed it for just $100,000. And part of that is because those mortgages, they're compounded monthly. And so whatever portion of the balance for that home that you haven't paid off, you have this extra interest that's being accrued on every single month. And so that's one of the reasons why banks actually like to give mortgages, because of course they get money up front, and then they're getting extra money every month too. And essentially you paid for your house twice. Okay. All right, so let's move on here to the next example. So for our next example, it asks, what is the amount of an investment after 6 years if the initial investment is $23,000 and that investment earns 13.5% in interest compounded continuously? Okay, so notice that since this says that we are compounding continuously, we have to use a different formula. Okay, we can't use what I'm calling the finite compound interest formula, meaning that the number of compounding periods is something that we can actually count. Whenever we say interest is compounded continuously, we're saying that n is approaching infinity in this case. Okay, and what we're really doing is trying to figure out, if I worded this problem another way, how it would read is, what is going to be the maximum amount that I can accumulate or earn from this investment if the time period was 6 years and the initial investment amount was $23,000 and the annual interest rate was 13.5. Okay, so what we're about to find out is, at an interest rate of 13.5% at 6 years, $23,000, this is going to be the max amount I can get. Okay, no matter what happens. So here we know that our initial amount, our principal P, is $23,000. We're going to have E here, and remember that number is approximately equal to 2.713. When you type this into a calculator, you actually want to use the calculator's version of what E is. You don't want to use 2.713. Okay, so there should be a button on your calculator that allows you to be able to actually have E typed in. Okay, and so here 23,000 E raised to the R, and of course this is going to be our R, and we're going to write that in decimal form, and then T is going to be 6 years, so we're just going to write that like that. Okay, and so if we were to tally all that up, then this would be 23,000 E raised to the 0.081, and if we put that in our calculator at that point, you should get out $24,940.53. Okay, so if you held an investment for 6 years, and the initial amount that you put into it is $23,000, and you know that you're earning 13.5% interest on that money, the max that you could get out of it is going to be this $24,940.53. And so one of the things that I try to tell the students that I teach is that this formula is good because it gives you a sanity check on knowing if some particular financial instrument, or a person selling you a financial instrument, if they're actually telling you the truth or not. Okay, so if they tell you, hey, if you invest $23,000 now and you leave it with me for 6 years at 13.5% interest, you're going to be able to earn $30,000. I'm going to be able to give you $30,000 or $40,000 back. Well, based off of this, that's not realistic. Okay, if it's just going to be a simple financial instrument where you just put your money there, it earns a certain amount of interest over time, and no one's doing anything to flip the money or anything like that, that in 6 years, the most you're probably going to get out of this is a little under $1,500. Okay, and that's just the difference in between this particular $24,940.53 and the $23,000 that you initially put into it. So you kind of have a way to know if someone's really trying to dupe you or not. Okay. All right. So let's move on to our next example. So for our next question, it says if an investment company is going to pay 6% in interest, compounded semi-annually, and so we know since that's semi-annually that means that our compounding periods per year is going to be 2. How much should you deposit now to have $10,000 10 years from now? Okay, so how much should you deposit now? What that's saying is, what money should I put in today? Or what should be my initial amount? So here it's the principle that it is that we're trying to figure out. How much should I deposit now so that I could have $10,000, which is going to be your future or accumulated amount 10 years from now? And of course, that's going to be your value of T. So we know that the 6% here, that's going to be our annual interest rate. We know what the compounding number of compounding periods per year is. We have the time. The only thing that we don't know is what the principal is going to be. So now if we write out this formula here, this implies that A is 10,000, and that equals P, which is what we don't know, 1 plus, and then we have R, which is going to be the 6%. So that's going to be 0.06 divided by 2, since we have 2 compounding periods, and that's going to be raised to the 2 times, and the amount of years is going to be 10. Okay. So once we have this, of course, we just need to solve for P. So if we work on this some more, we'll see that we got 10,000 here equals P times, and this particular amount here, let me do this in a different color, that's just going to be 0.03 there. So inside the parenthesis, we'll have 1.03, and that will be raised to the 20. And so now to solve for P, all we need to do is just divide both sides by 1.03 raised to the 20. Okay. Now, here if I write that, that just means that here we have 10,000 divided by 1.03. All that raised to the 20 is going to equal to P. And notice that we could also write this as 10,000 times 1.03 raised to the negative 20 because of exponential rules. And specifically speaking here, if we use the exponential rule that a raised to the negative n is the same as 1 over a raised to the positive n, then we see that this 1.03 that's in the denominator being raised to the power of 20, and let me fix that there, that this just looks like 1 over 1.03 raised to the 20, kind of like what the right hand side of this looks like, and we can rewrite it this way. Okay, so now all we have to do is put that into our calculators to get what our answer will be, and this answer here should be approximately $5,536.76. Okay. So we see now that we're going to have to put in $5,536.76 now to be able to get 10,000 later, but of course that's 10 years from now. Okay. And so you see 10 years from now, you've almost double your money. Okay, because doubling your money here would be like $11,072 or $73 dollars, and so yeah, so that would be the amount there, and that seems about right. Okay, at 6%, you should probably double your money. You should double your money probably about every 12 years. And so there's this rule called the Rule of 72 that kind of gives you a quick and dirty way to be able to figure that out. And basically all it is you say 72 divided by the percentage rate that you have. And so let's say if that's equal to 6 in this case, then we know 72 divided by 6 is 12. Okay, and so that pretty much lets you know, rough wet thumb in the wind estimate, as we like to say. That kind of lets you know the amount of time that it's going to take for you to take a certain amount of money and double it. And so whenever I do problems like these, once I get my answer, I kind of say, okay, well, does that kind of fall in line with the Rule of 72? Okay, and so we see that, you know, this one is, because we're about 2 years off, and we're about $1,100 or so off from doubling this particular amount here, so it makes sense. So for our next example, we want to know what is the annual percentage yield, also known as the effective interest rate, for a certain amount of money invested at an annual rate of 3.9%, and it's compounded monthly. Okay, so what we want to know here is, if we put a certain amount of money into this investment that pays 3.9% and is compounded monthly, what's the actual percentage rate in interest we're going to get in terms of how much money I put in versus how much I would get out. Okay, and so to do that, we could use the annual percentage yield formula, which we know is also this little r sub e formula here, and that's just going to be 1 plus r over n, and all that raised to the n minus 1. Here we know that this 3.9 is what r is. We know if we're compounding monthly, then that means that n is 12. Okay, so we're here, and we just say 1 plus 0.039 divided by 12 raised to the 12 minus 1. Okay, and so in doing that, that first term here would just end up being 1.00325, all that raised to the 12 minus 1. And if we were to put that into a calculator here, this would be 0.0397047327. Yeah, kind of wrote that funky, so let's change that. All right, 7327. Yeah. And of course, that's roughly about 3.97% if we wanted to round, express our answer in percentages and round the 2 decimal places. So notice that we're earning about 7 extra percent on our money, just because of the fact that it's compounded monthly. Okay. And of course, depending upon, you know, what the actual dollar amount would be, that would depend upon, you know, how much extra that would be. If it's $1,000, then of course 7% of $1,000 is not that much. But if we're talking about $1 million, 7%, you know, is a lot. So it also depends upon how much money you're actually dealing with. All right, so let's move on to the next example. So for our next example, we're going to see how we can actually figure out the particular time for an investment based upon an initial amount we want to put into it and a target amount we want to get out of it. Okay. So here it says, how long will it take $5,000 to grow to $7,000 if it is invested at 6% compounded quarterly? So here, again, we know since it's saying compounded certain number of times a year, we need to use our finite compound interest formula. And here our A in this case is going to be 7,000 because that's the amount that we want out. The P is going to be the 5,000 because that's the amount that we're willing to put in. Our interest rate is going to be 6%, and I'm just going to write it as 0.06. And N, since it's quarterly, will be 4. And of course, the thing that we don't know is the time. And whatever the time is, once we solve this, it's going to be in years. So note here that in order to solve for time, we're going to eventually have to introduce logarithms into this particular situation because we have technically an exponential equation here. And to be able to get this t out of the exponent, we would have to use logarithms to be able to do that. So this is an example of seeing how that would work. So knowing that we have all this information here, A again is 7,000. That equals to P, which is 5,000. 1 plus R is going to be 0.06 divided by 4. And all that's going to be raised to the N, which is 4 times T, which is the thing that we don't know. So the first thing that we can do here is we eventually want to get this term 1 plus 0.06 divided by 4 raised to 4t. We want to get that by itself, okay? Because we're not going to be able to use any logarithm properties cleanly until we do that. So here, the first thing that we can do is just divide both sides by 5,000, okay? And so by doing that, of course, these 5,000s will reduce to 1, and 7,000 divided by 5,000, that will just be 7 over 5. And I'm just going to keep it in fraction form. Now, on the right-hand side, what's left, you end up having this 1 plus 0.06 divided by 4, and that's just going to end up being 1.015. And all that raised to the 4t. So from here, we're going to use a logarithm property called the log of both sides, or a log of both sides theorem. We can do log of any base that we want. Probably the two most common bases to use is log base 10, which most of you know is just writing log like this. Whenever we don't have a number in the subscript there, it's assumed to be log base 10. So what we'll be doing is we can either do log of both sides like this, or we can do log base e, which we better know as the natural logarithm, or ln. We can do that to both sides. For what I'm going to do here, I'm going to choose to use the natural log of both sides, just because that's the one that I do most common. But you can do log base 10. You can actually do log base 1.015, and I'll actually work this again to show you how it would look differently if you did that. But traditionally, we would just say natural log of both sides here. And then once we have it written like this, one of the things that we know is that there's another logarithm property, and that logarithm property is if we have log base a of something raised to a power, we could rewrite that this way. And so essentially, what it's saying here is that we can take this exponent and pull it out. And if you have something being multiplied times a logarithm here, you could actually take that and put it back in the exponent. So like, for instance, I could have taken this 5,000 here and actually put it back here and made this 20,000t if I wanted to, okay? I chose not to do that because I wanted to deal with smaller numbers, not bigger ones, okay? So with that being said, if we move forward here, I'm going to kind of go horizontal here for a second, then I know that I can take this and put it out in front. And so now I'm going to have, oops, didn't want that color, so let's change that. All right, so we have natural log of 7/5 is equal to 4t times natural log of 1.015 raised, and that's it, yeah, because I already put it down. So here at this point, notice that I have a 4 times a t times a ugly looking number called natural log of 1.015, okay? Now I'm going to rewrite this because since all of this is multiplied times each other, what I could do and what I could have done here to make life easier is just to bring down the t and leave the 4 up there, okay? I could have done that, okay? Traditionally, you don't see it, but we could have actually done that. In general here, what I'm going to do is I'm going to rewrite this. And I'm just going to say that this is going to be 4 times natural log of 1.015 times t, like that. And here I'm going to put this in brackets. Now, the only reason I'm doing that is because I want you to realize that 4 times natural log of 1.015 is just a number, okay? That's all it is. And what I want to do is solve for t. And so now that I'm here, my last step is just to divide both sides here by 4 times natural log of 1.015, okay? Now, I'm going to do, before I do that though, I'm going to rewrite this slightly different. And the reason I am doing it this way is that whenever you plug this stuff into a calculator, you will end up making less mistakes in getting what your actual answer is if you keep this 4 here in the exponent versus when you just leave it multiplied, okay? And it has something to do with order of operation. If you actually know what you're typing in, you'll get it right. But if you type it in wrong, then you tend to get answers that are off. And so here, by putting that 4 back into the exponent there, you're kind of forcing yourself to get the right answer, okay? And that's just one of the things I've picked up in doing a lot of these problems. So at this point, all we need to do is just divide both sides by this natural log of 1.015 raised to the 4. So let's go ahead and do that now. Yeah, it's not writing correctly, so let me just try to start over. Okay, so we have that. And then from here, we know that on the right-hand side, all of this is just going to reduce to 1. and our result will be t on the right hand side. And here we would just have what you see above. So just natural log of 7/5 divided by natural log of 1.015 raised to the 4. Okay. And I'll rewrite this way. And here at that point, we can just plug that into our calculators to get final answer. And here, what we can do is we will say that the actual answer that you're going to get is this. Okay. Now, the problem with this particular answer here is that remember that your time is going to be measured in quarters. Okay. So what that means is that, let's say if we were in year 1, then we would go from 0 to 0.25, and from 0.25 to 0.5, and from 0.5 to 0.75, and from 0.75 to 1, because we're doing it in quarters. We know that 0.65 is not a quarter of a fraction of a year. So whenever we see situations like this, since this particular investment here is compounding quarterly, you won't get this. You won't get the actual $10,000 as the accumulated amount until you go to the next compounding period. In reality, it'll actually be a little bit more than $10,000, but at least you'll have $10,000 in there. So I'm saying all that to say is that you have to pay attention to the compounding period to be able to answer these kind of questions correctly. So although the actual answer is about 5.65 years, the answer that you want to give is 5.75 years. Okay. And what you're showing here is that you're taking into account of the actual compounding period, because at 0.65 of the 6th year, you'll technically reach 10,000, but it won't be awarded to that investment until after you've basically gotten to the end of that 3rd quarter there. Okay, so that's why the correct answer would be what you're seeing here at 5.75 years. Okay, so for our next example here, we're going to do another situation where we're trying to find time, but now we're going to do it for some investment, but we're looking at the compounding being continuous. So therefore, what that means for us is that instead of using the finite compound interest formula, we're now going to be using what we nicknamed the PERT formula earlier. So we want to know how long does it take $42,000 to grow to $60,276. So just based off of that, we know that this is our initial amount P, and the $60,276 is going to be our accumulated amount. So how long will it take $42,000 to grow to $60,276 if it is invested at 4.25% compounded continuously? Okay, so of course, invested at 4.25%, that tells us what our interest rate is, and compounded continuously just lets us know that n approaches infinity, which means we're going to use this PERT formula here. So therefore, we know that A is equal to P times E raised to the RT. That implies that we have the 60,276 equal to 42,000 times E, and then that's going to be raised to the R, and this R, we're going to put the interest rate in decimal form. And then of course, T is the one thing that we don't know. So whenever you see how long here. Of course, that's letting you know time. All right, so the first thing that we need to do here is divide both sides by the 42,000. And so for that one, I'm just going to keep this number as this fraction here and carry it all the way to the end, because I really don't feel like trying to figure out what that actually is. So if we do that, and here what this means, if we kind of just keep on going here, is that we have 60,276 divided by 42,000, e raised to the 0.0425t. And now what we'll do is we'll actually take the natural log of both sides here, okay? So our next step, what we'll do is we'll take the natural log of both sides. I'm just going to leave a space for it here. So this will be the 60,276 divided by 42,000 here. And this will be e raised to the 0.0425t. Okay. Now, with this being said, the right-hand side here, notice that natural log of e raised to the something, and I'm going to write it like this, natural log of e raised to the x. This is the same as saying log base e of e raised to the x. And we know that there is a logarithm property that says anytime we have log of some base and the argument on the inside of the logarithm is an exponential with the same base raised to the exponent, whatever the exponent is the answer. So what this lets me know here is that all of this just simplifies to 0.0425t. And so if we carry on here, let's go here. So now we know that we just have natural log of this 60,000. This pen is starting to really act up. Sorry about that, y'all. The 60,276 divided by 42,000, and that's just equal to what you see here. And then, of course, the last thing that we want to do is just divide both sides by the 0.0425. And that will get us what we need for our final answer there. All right, so if we do that, then we'll see here that this and this reduces to 1. And all we have left is this t here on the right-hand side. So here we will have natural log of all this business again. All over 0.0425, and that's equal to t. And now if we put all of that in our calculator, then this will come out to be roughly 8.5. And of course, since we're talking about time, we're talking about compounded interest, continuously compounded interest in this case, the time has to be in years. And so that would be our final answer for example number 8. All right, so let's move on to our last two examples. So for example number 9, we're back to looking at the annual percentage yield or effective interest rate type problem. It's just worded differently. And so in this example, we're just asking, based upon 2 investments that you're given to choose from, which one is a better investment and why. And so we're going to start off with the answering the why first. We know that whatever answer we end up with, the one that's going to be the better investment is the one that's going to have the higher effective or true interest rate or higher annual percentage yield. So what we need to do is figure out, based upon the formula that we know for annual percentage yield. I'm going to go ahead and write it here. Based upon this formula here, we need to substitute in what we need for each investment and then figure out which one is going to give us a higher value. So let's look at the APY for investment 1. And we have 1 plus, and for R, of course, that's going to be the 9%. So we're just going to say 0.09. N, since we're compounding monthly, that means N is 12. And we're going to raise that to the 12 and then minus 1. Okay. So for the next one, investment 2, kind of the same thing. So, of course, the interest rate now is 9.3%, and we're compounding annually, so that means N is 1. That'll get raised to the 1, minus 1 there. So once we have these, if we actually put all this into our calculator here, and I'll start with this first one, we would get 1.0075. All that raised to the 12, and then minus 1, and this would end up being 0.09380,68977, and that's roughly about 9.38%. Okay, so for investment 1, you're told that you're going to get an annual percentage rate of 9%, but in actual interest, in terms of how much money you put in and how much money you get out, it's going to be about 0.38% more. Okay, so now let's look at investment 2. So for investment 2, of course, this is just 1.093 raised to the 1 minus 1, or we can simply just say 1.093. So no need to get fancy there. And we see that this is just going to be 0.093 or 9.3%. Okay. And so we see here that based upon what we're looking at, investment 1 is better. Okay. And so what this teaches us is that, again, we have to not only pay attention to whatever the interest rate is, we have to pay attention to how often it's being compounded. Because we see that investment 1 had a lower interest rate, but it was compounded 11 times more per year than the investment with the higher interest rate. And because of that, the one with the lower interest rate actually ended up being better. Okay, so again, hopefully this is a lesson to make sure that you pay attention not only to interest rates, but to compounding periods as well. All right, so let's look at our final example. So for example number 10, we want to know how long it's going to take a certain amount of money to double if it is invested at various annual nominal percentage rates compounded over various times per year. And so example A here says that the annual or nominal interest rate is going to be 12%, And we want to compound quarterly, which means we want to compound 4 times per year. So we're going to do example A traditionally, but eventually we're going to discover a shortcut here that we can use to kind of just get straight to the point. And I want you to I'm going to go through this the traditional way so that you can actually see it. So notice that here we have what R is. We know here that N equals 4. Okay. They haven't given us what A is, and they haven't given us what P is. But all we know is that whatever P is, A is going to be double that. Okay. So here, P is a certain amount. We know that A has to be twice that. So if we use this in our formula here for compound interest, we know here that this amount is just going to be 2P. Okay. So if we do that and we take note of it, then we know that 2P is equal to P times 1 plus, and then this will be 0.12 divided by 4, and all that raised to the 4 times T, because that's what it is that we're trying to figure out how long it will take. Okay, so I'm just going to write this as 4T. So from here, again, we want to get T by itself. And so the cleanest way to do that is to first divide both sides of this equation by P. And if we do that, notice that we just have 2 on the left-hand side, and we're going to have 1.03 raised to the 4T on the right-hand side. From there, we can do like what we did before in taking the natural log of both sides. So here, this will just be 2 on this side, and this will be 1.03 raised to the 4T on this side. Okay. And so like I mentioned before, since we just want T by itself, we can use our logarithm property here that allows me to take this T and put it out in front, and I can really leave that other 4 in the exponent because it's going to make it easier for me to calculate things later on. Okay. So once we're here, then this is just going to be natural log of 2 equals T times natural log of 1.03 raised to the 4. And now all we have to do is just divide both sides by the one thing that we don't want on the right-hand side, which is everything except for T, which is this natural log of 1.03. Sorry. Let me rewrite that correctly here. Yeah, because the 1.03 should be the only thing raised to the power of 4. We'll do the same thing here. So once that's done, of course, on the right-hand side, we know that all of this reduces to 1. We'll just have T. On the left-hand side, we'll just have that natural log of 2 divided by natural log of 1.03 raised to the 4. Of course, once we do all of that, a final answer here actually ends up being 5.86 years. Okay. Now, again, since we're doing things quarterly, the only possible answers that we could have for year 5 is either going to be 5, 5.25, 5.5, 5.75, or 6. And so since 5.86 fits in between 5.75 and 6, our actual answer here should just be 6 years. Okay. So here what I'm going to do is just come here and say we're going to round that up to 6 years. And that's because in a real situation here, you would have to wait until the end of that particular compounding period for you to be able to actually get that doubling of the money, and you'll get plus a little extra. Okay. All right. So let's move on to example B. So it's kind of the same setup. The one thing that's different now is that now we're compounding semi-annually, and the interest rate, the annual interest rate is 8%. So again, we start off with 2p is equal to p times 1 plus, and here this would be 0.08 divided by, since it's compounding semi-annually, n is 2. And that will be raised to the 2t. Okay. Now, if we divide both sides by p again, like how we did before, what we're going to end up with is this. Okay. Now, the thing that I want you to notice at this point, and I'm going to put this in red here, is that what you're looking at here and what you end up looking at here, that setup is very similar. Okay. So notice that how you start off is pretty much going to be the same. And so what's going to turn out here is that when we solve this, the way that it's going to look at the end of the day is going to be the same too. Meaning, if we look here, we already know what the end setup is going to be as well. Okay. So if I went through the whole, thing of kind of working through this problem again, what I'm going to see is that t is just going to be natural log of 2 divided by natural log of, in this case, 1.04 raised to the 2. Okay, it's going to be the same exact thing. And so from there, of course, I could just calculate this and get the answer here, and I'll go ahead and tell you what that is. So this is roughly 8.83 years. And again, since we're talking semi-annually, either the only answers that we could really have here realistically are 8, 8.5, or 9. And since 8.83 is in between 8.5 and 9, we choose 9 years as being the actual realistic answer. Okay. So at this point, the other thing that I want to illuminate here is that there is actually a shortcut for us to get to know, all right, well, how long is it going to take for a certain amount of money to double? Okay. And there's this relationship in between the time and whether you want to double, triple, or whatever. Okay. And I'm going to give you that shortcut formula now for whenever we want to double something, so that we can kind of skip some of this other stuff and just get straight to the point. All right. So the shortcut here is that if we were talking about, we'll say the doubling time, and I'm just going to call it t double like this, then we had a situation here where we're given the number of times that the investment is going to compound per year and the interest rate, we could simply just say this is going to be natural log of 2 over natural log of 1 plus r divided by n. And of course, this 1 plus r divided by n would be raised to the n, and all that would be inside of the logarithm in the denominator. Okay. Now, I'm mentioning this because if we were in a situation where we wanted to figure out, well, how long will it take for a particular investment to be cut in half, let's say if it's losing money for whatever reason, then here we could say t half is going to be, and in this case you would have a negative natural log of 2 over natural log of, we'll kind of do the same thing here. Okay. And so lastly, if we had a situation where, let's say we wanted to figure out the time that it's going to take for a certain amount of money to, let's say, triple, okay? Or let's say if we wanted to say, all right, well, we want to figure out how long it's going to take for it to get cut by a third. In general here, we could use this formula. And so I'm just going to say this is t sub n, where this would be natural log of, oh, sorry, let me not use n because we already have n. Let me use another variable. So I'll use z. No, not z. I'll use m. Yep, m would be good. So here this would be natural log of m over natural log of 1 plus r divided by n, all that raised to the n. And of course, m is going to be whatever amount you're trying to get it to double or decrease to. So let's say if you're trying to triple your money, then m would be 3. If you're trying to figure out a third of the money, instead of having it, you want to figure out, well, how long is it going to take for it to decrease by 33% or a third, then you would let m equal 1/3 there. And that kind of goes with this case here, because if I take the numerator here and write this as natural log of 1/2, let me erase this stuff down here so this doesn't get confusing. So if I take natural log of 1/2, know that because of our logarithm properties, I can actually take this and rewrite this as natural log of 1 minus natural log of 2. And we know that natural log of 1 is just simply 0. So that's how we got the minus natural log of 2 there. So the general formula here for being able to figure out situations like what we've been asked is to essentially just remember this particular formula here, and that will kind of cut to the chase and get what it is that you're looking for. Okay. All right. So with that being said, we're going to do this very last example here, where since we are compounding continuously, now we need to use the PERT formula. Okay. But here we know that this amount here is still going to be double. Okay. And so if we do that, of course, the interest rate here is going to be 33%, and compounding continuously, we know that the E sort of takes care of that. And for T, let's remember here, that's the thing that we're trying to solve for. So pretty much got everything that we need. So here we would have 2p is equal to p, e raised to the 0.33t. And of course, if I divided both sides by p here, this would just end up being 2 is equal to e raised to the 0.33t. And then again, I could take the natural log of both sides here. That's kind of the traditional way of doing it. Another way that I could do it is just directly translate from exponential form to logarithmic form. If I did it that alternative way that I'm talking about, then we would have to do it like this, where this would be your a, this would be your y, and this would be your x. So if we translated it that way, and I'm just using the definition of a logarithm here, then this would just be 0.33t equals log base e of 2. Okay, so if I did it that way. If I did it the more traditional way of just taking the natural log of both sides, I would have natural log of 2 is equal to natural log of e raised to the 0.33t. And note again that anytime I have natural log of e raised to something, it's going to be equal to whatever that something is. So my point here is that we still get to the same place because here log base e of 2 is the same as natural log of 2. Okay, so no matter how you get there, if you want to do it like way number 1, or you want to do it way number 2, no matter how you do it, you'll eventually get to the point where you're saying that you have 0.33t is equal to natural log of 2. And to get our final answer, we just divide both sides by natural log of 2. And of course, if we put this in our calculator here, we'll get roughly 2.1 years. And since we're compounding continuously, we can leave it exactly like this and just say 2.1 years, since in reality, compounding continuously means that every moment of every day, we're getting interest paid upon interest, paid upon interest. Okay. All right. So I know this was a very long video, but I wanted to make sure that I had all the examples in one place for this particular version of applications for exponential and logarithmic functions. So the part 2 video is going to go into how we actually use exponential and logarithmic type of functions for things like population growth, radioactive decay, measuring atmospheric pressure, things involving the Richter scale, decibel scales, whatnot. So we're going to see a lot of those examples there. So if you need to learn about how to solve and be exposed to such problems as those, please check out the part 2 video. And again, thank you for watching this one. Take care.